there is a small correction to what I did. Series 1, correction to what I did last week. I proved the following. If M of which meaning it admits minimal projection, that's what it means. Then we proved that, when it's not entirely correct. I said that then there exists Hilbert H naught and K in a unitary between H naught tensor K to H such that 1 and plus B of K U. In this, I assume this K to be L2 of N, which need not be correct, of course. I mean, there was a collection of projection P1, P2 up to that. That can be finite also. Can be at most countable. It will not be uncountable, but it can be finite also. So when it is finite, it will be just a finite set. It's not L2 N. That's all. So in that case, it will be finite dimensional. We will have M and C. The K is in that case, this K will correspond L2 of 1 up to N. It's just Cn, of course. It's just Cn. So in that case, it will be Cn. And in this case, this will be M and C. And this will be isomorphic to matrices. Okay. So that's all. That's the correction. I had P1 up to Pn. I assumed that it's countable. It may not be countable infinite. It can be finite also. So this thing say that if M is a type 1 factor. So first, that's the statement. So M is a type 1 factor. One factor. Then M is isomorphic to, under the isomorphism equal to M and C for some N. Can I where H is isomorphic to B of H, where H can be finite dimensional or infinite dimensional. Okay. So this also implies if G is a group, G is a ICC group, then gamma of G is not type 1. First, it's a factor. Gamma of G, when it is ICC, it's a factor. Okay. And it is not the type 1 because gamma of G admits a trace. And B of H cannot, it's infinite dimensional. When G is ICC, infinite conjugacy class group, then it will be infinite dimensional and it will be a factor. And it cannot, first of all, it does not admit any, isometries, for example. We proved that it cannot have isometries, number 1, or it admits a trace. And trace is not, you cannot define a trace on infinite dimensional B of H. Because of that, this is gamma of G will not look like B of H. It will not look like 1 B of H also. But not define a trace on this also, but there is a trace on that. So because of that, gamma G is not, it's not type 1. So we get a non-trivial example of non-type 1. Okay. So if it is type 1, it has to be isomorphic. It's not isomorphic. Based on this, you can bring it back by this P, you can bring it back. Okay, there are type 2, type 3, and we want to discuss more specifically type 2. For that, we want to make a few definitions on projections. We want to classify. And PQ projections. This is my notation of projection. Okay. We say is equivalent to Q. This is usually what is called Murray-Van Neumann equivalent. Okay. I mean, they are the one who studied some series of papers called ring of operators, one, two, three. So their study this thing, and that is when the sequence is defined. Such that U star U equals P and U. These projections are connected by this partial isometry. And this is partial isometry. This kind of partial isometry is a purely non-commutative phenomenon. The commutative phenomenon, suppose if we have two sets, commutative, of course, that looks like set. Okay. If we have a U, okay, then uh, it's a unitary among within that set only. It cannot intertwine to different projections. Okay, it will be okay. So this is you have this one-dimensional projection or some projection. You have different orthogonal projection will look like this, some block. And this block, something here, will be the partial isometry between them. Okay? That's how we should remember. This is the, we'll just verify this is an equivalence relation. Partial. I mean, it is just identity, it's also a projection, it's also a unitary, it's all project. Partial isometry is like a unitary projection. If you just restrict to this as domain, that's as the, it is just the unitary between them. Any projection is also unitary between itself. Okay, it's just identity on that. So, so P is equivalent to P and P is equal to U. If U is equal to P and U are equal to Q and V projections. Now take which one you want to take? So we want to take U star, V star, U, V, U, right? So take W equal to V, U. Okay? That will be the, that will implement the equivalence between P and R. So if we U equal to U is 0. I mean, outside U star is 0. It's just a unit limit. Here to it's here. So once you restrict the whole thing to here, you verify that I mean, R U Q is also U U star. So if you use that, another property of the partial isometry. So if you use that, you just two collections of project. Projections, you can add it up. Okay, I mean, if it is finite sum, there's no confusion. Even if it is infinite sum, we can add and it will converge strongly. Okay, I mean, you just write it down. You take any vector in the direction. You take the, I mean, that will be the, I mean, if you take the sum, that will be the exactly this generated by that. Okay? Or you can take increasing union P1 Pn. This will be increasing union. Okay, and that will be precisely the sum, and it will be just the union of all these things. Okay, so the convergence works. Okay? So this thing should be very clear to you. I mean, very familiar to you. Okay? I mean, when we take sum of orthogonal projections, that converges. So then, and it will be you can write it as direct sum also. I mean, there is no notational problem. It is direct sum. Pn is equivalent to Qn for all n. Direct sum n. Should I write the proof or it's Pn star equal to P and Q, okay. Then you take the summation UN, which is actually it's a unitary on one subspace, it's zero outside that subspace, right? That is it's an orthogonal subspace. This will also converge this. This will converge. Then this will converge, this strong convergence. Again, strong convergence. They leave it as you can verify. You take some vector in the orthogonal direct sum, okay, and each one of the middle converge. Okay, you can easily verify that it will converge. Then u star u equal to that P and u star. Okay. So if you have orthogonal things, you can just do that. And it's always the case whenever you have orthogonal projection. And if I have unitary, if we have partial isometry between here, that means it's just unitary from this kernel perp of a range of P1 to range of Q. It is just the unitary between them. We can just write this unitary. You can do anything you want. Okay. So then you get partial symmetry between between this collection. I mean this sum and this. I want to use is the following. So next I want this is a partial order. We have defined an equal on a phenomenal algebra. This is a partial order. We have partial order between projections. Okay, that's not a total. Clearly, that's not a total order. We want to get a total order on factors. So we define the following PQ or projections in M. And I less than or equal to curve if there exists, I mean, if there exists a P naught contains less than Q, this is the usual partial order. This is the range of P naught is contained in the range of Q, or you can use the partial order on the self-adjoint operators. Okay, P naught is contained in Q such that P is equal. This equals is this equal. Maraivan, I mean, okay. That is, there exists partial isometry U in M star U equal to P and U star is less than or equal to Q. That's all. P is equal to some P naught, which is under, which lives under, whose range lives under Q. Okay. So total order, when it is a factor, we'll come to that. Okay. So first property, if this should be clear, if P is less than Q and Q is less than R, then P is less than R we have to do. This just that there exists a, I mean, this shall I leave it as an exercise? Orally, I say that and leave it as exercise or assignment. I haven't given assignment. I ask you to write this as assignment, just this property. The other property, other partial order, I will ask you to do just this property, just that you understand everything on partial isometry. It just says that there exists a partial isometry such that equal to this and something. No, there exists a partial isometry such that U star U equal to P and U star lives less than Q. And there exists another V such that V star V equal to Q and V star V is less than R. Then you compose it and then you get this. It's very clear, right? Just okay, huh? I know it's okay. Okay, it should be clear. If it is not clear to you, write it as an assignment. Okay. It's clear, I think. So what is non-trivial is the following. So next we want to prove. So we need to prove the following. We need to prove if P is less than Q, Q is less than P. I mean, this is a partial order where the equality is with respect to the equivalence. It's not equality, it is just then P is equivalent to Q. That's what it is. I mean, with respect to this is partial order, where we identify projections up to these equivalence. Okay? It's not up to equality. This we want to verify. You know this, what is called Schroeder-Bernstein. Huh? Yeah. I'm not, I mean, able to comprehend. You, what did you say? Schroeder-Bernstein. Yeah, if you have a bijection between the x2, if you have an injection between x into y and y into x, then there's a bijection between them. Same thing. Yeah, correct. So that's what you want to prove. So we have P is left. So there exists the U partial isometry, U V in M partial isometry, such that U star U equal to and U star is less than, this is the usual less than Q, and V star V equal to Q, and V star is less than P. Okay. Now we want to, it's the same proof actually. If you have, I don't know whether you have seen this Schroeder-Bernstein theorem. You will have a injective map from x to x into y, two sets x and y. If you have an injection from f to x, and you have a g from, this is also an injective map from here, then there is a bijection between them. Okay. So whatever you do, you will do for projections here. Indeed, when you have all this, I mean, that's what we will do. I mean, more or less the same idea we'll use. Okay. Okay. So have you seen the proof? Schroeder-Bernstein, you have seen the proof? Okay. Then you will get a sequence, disjoint sequence, and you will write something, no? The same thing you'll do. So, yeah, maybe I'll do. So, inductively. Call it P1 equal to V star V. V star QB also, right? Which is V star QB also. I mean, I'm writing it for the purpose because I want to define inductively. So that we have Q1, which is equal to U star. No, V star. No, V star V is Q. So V star. V star equal to V Q V. P to Q is U. I mean, where U star U equal to P. U star is that. So U is also equal to U P U star. This is P1. And just writing here, I write first Q2, P2 equal to V Q1, Q1 V star. And P1 U star. Okay, Pn equal to I've called this P0. So U V Q n minus 1 V star. Okay. And and it's clear that this containment is clear, right? Of course, this is clear. Of course, by whatever, by our assumption, V star lives inside P. Okay. And then this map, P going to, for any projection, VP V star or UP V star, this kind of map respects the positivity. And I mean, if P is greater than Q, then VP V star is greater than VP VQ V star for any P and Q. This is, I mean, you can verify. Okay. So because of that, here this is, I mean, you are and Q0 in that add V operation, okay, Vx V star, whatever, in that operation that comes contained here, that will contain here. I mean, that's a projection, it has to contain it. Okay. For projection, this less than or equal to, well, I mean, the containment less than or equal to, if you assume that containment or the partial order of self-adjoint, both are same. Okay. So it's clearly a decreasing sequence. Okay. The decreasing sequence. So you call P infinity as the intersection, the okay. I mean, we don't care whether it is 0 or something. We just take things. We do it continuously. Maybe it will stop or something, but it doesn't matter. Okay. So all this similarly equal to all this Q. V equal to P and the substrate. Partial something between that. So because you just yeah, that doesn't matter. Okay. I mean, because it's in equal to So equal to Q infinity. Okay. U P infinity. Okay, I write it like this: P infinity, U P infinity, U P infinity star. I write like this, which is equal to Q infinity. I'm just rewriting the same thing. U P infinity U star. P infinity is a projection, so I can write it 2 times A1. Okay. This is equal to this. And similarly, if you take U P infinity star, U P infinity, which is equal to P U star U P infinity. Okay. But U is P. Okay. P is a bigger projection. P infinity is contained in P. Okay. P is the bigger projection. So this P infinity is equal to Q infinity. Okay. Sequence P infinity is equal to Q infinity. Now we have to do something about this. But this is a decreasing family. But if you subtract this, you take P minus P1. P minus P1 is orthogonal to P1. Right? You just write it P minus P1 times P into P minus P1 and P1 commutes, and P minus P1 times that is equal to 0. Okay? So that means it's orthogonal to each other. The range is orthogonal to it. P and Q have orthogonal projection if PQ commutes and PQ equal to 0. So from that it follows. Huh? Huh? Yeah, sure. Yeah. My if you take this, P will remain. You just it's P infinity all these things, and then similarly equal to the other minor, I mean, all the intersection. We want to show that P is equivalent to Q. That's what we want to show. We have assumed that P is less than in this partial order. We have assumed P is less than or equal to Q. Q is less than or equal to P. We have to verify is equal to Q. Already is equal to this sum. That's what you have to do. Directly you cannot show because P minus P1 will go. Okay. See that U as 2 of U minus star. Okay. On the other hand, of course, star into P minus P. Q for n equal to 0, 1. It starts from 0. Okay. This is Pn plus 1 minus Pn. Now you write it like this. P minus P plus P minus P1, P1 minus P2 will be Q. Because this is equivalent to this. Okay. But then this is equivalent to this. So this two sum is equivalent to this. You do that very well. Okay. So you can write the detail. This implies summing plus P will be equivalent to sum. The next thing only contained in Qn. Qn plus 1 is contained in Qn. It's decreasing. So you cannot write it the other way. Qn minus Qn plus 1 is Pn plus, here should, sorry, Pn plus 1. So I'm saying you take this here. If you apply only V, it will go like this. It means this whole thing will be like this. But instead, what you do is you take the odd one to like this, and even one to like this, whatever. Okay. So then you get a bijection between them. It's the same idea in Stoddard-Bernstein motion theorem. So that's all. This implies P is equal to Q. Okay. Okay. So now we have proved it's a partial order. Now we want to define what is called finiteness. We have already discussed this. P in M is finite, let's say infinite, if P is equal to some P naught, which is greater than if a set is infinite, if it is onto a bijection onto a proper subset. Okay. So it's the same idea. Projections are like sets, quantized sets. Okay. So P is equal to P naught. Rx is a sub projection. Not equal to 0 is clear because it cannot be equal to 0. Non-zero projection cannot be equal to 0 projection. From that partial symmetry, you will get it. So is equal to P naught, so which is also not 0 if you want, right? Not equal to 0, which is a proper sub projection. So of course, P is fine. It's not same. Is any proper sub projection which is equal to P, then it is called a finite projection. Okay. Is an easy observation. Suppose a remark, call it if it's less than Q and Q is finite, And P is assume P is finite, Q is finite. Suppose when we have to prove if P is infinite, then Q is also infinite. Okay, suppose P is infinite, that is, and U star is equal to P naught. Okay. So let's write it as a diagram, it will be clear. That is why I write this diagram, which is nonsense, of course, notation wise. Hilbert space does not look like that. Just we decompose, just for our you, you have P, so this and this is P, and you have P naught contained in this. Okay. Now P is so let's write it here. Okay. This is P naught. Now you have a function, you have a partial isometry from here to P naught. Okay. Something here. Okay. Now you this is starting from here, something happening here. Okay. Now you define a partial isometry, which is defined. This is an orthogonal space. Write it like Q per range of Q per, okay, direct sum range of Q, which is range of Q minus P, right? Q minus P, range of P minus P naught. Okay. So now you define U. I mean, if you have a U like this, define from H to H. That's the V restricted to Q per is 0, of course. And V restricted, or you can just commit. Yeah, and V restricted to Q minus P is identity. This U is 0 on Q minus P. U is 0 on Q minus P. And here V restricted to this P minus P naught. P minus P naught is just U again. No, V on P, sorry. This is this on P. You don't need, I mean, Q minus P, P minus P naught is not needed. P minus P naught means I have to write P naught also for that. So, okay. On P, it is just U. I mean, it is just U direct sum identity, direct sum 0. Okay. This will give a partial isometry between this will now this V star V will be equal to Q and V star equal to again P naught. Wait. No, if it cannot be identity, no. Yeah, it's okay. Its identity means yeah, it doesn't matter, identity. So it will be 0 here. I mean, this will not be here. Range of, I mean, this is equal to P naught plus Q minus P. Okay. Between Q minus P and just its identity. So, or you can take it, okay. So I am having it as Q minus P. You can define it in different way also if you want. Okay. It's clear, no? I mean, you have a U which takes this P to P naught. I'm defining Q and you am defining a V which from here to here it is just identity. And here it doesn't, I mean, and this thing it takes to P naught. Still not be part of that. So that will be still a sub projection of Q. So Q is, I mean, equivalent to some Q naught, which is equal to this, which is equal to this, which is strictly less than Q. So Q is also infinite. So if P is infinite, Q is also infinite. Okay. If you have doubt, you write it and then you can, okay. I mean, it will be clear. That's the only way to familiarize if we are not familiar. Bigger projections. So the following is class, not the classification. This is the division. Classic. See, in mathematics, classification means you divide the whole thing up to equivalence class, where each one you will show that each equivalence class. I mean, you define an equivalence relation so that they are in the equivalence class or something isomorphism or something. They are all isomorphic, and then you provide an invariant for that, which will distinguish them. Okay, that's what classification is. This is what is division. We are just dividing. Okay, we should be careful. That's all. So these are the definitions. M is type 1. We have already defined. Two, it is type 2 if it does not have minimal projection. Minimal projections or finite projection. Minimal projection is something which does not contain any projection, any proper projection. Of course, obviously, it cannot have something equivalent to that also. So its minimal projections are certainly finite projections. So it does not have minimal projections. This is type 2. Type 3, there is no finite projection. Okay. Which is equal to that. Proper subprojection is equal to that. So such an example. Example of isometry. Huh? Isometry. I mean, shift will be the only example. Isometry is perspective. Not something easy to prove, but that's the theorem. Up to unitary equivalence or something. If there is a isometry, if there is an isometry S, then you can write the Hilbert space as something direct something K or some L2 N. So what is next? So we want to prove the following. Okay. We there's a recording. I mean, phenomenology is finite if identity is finite projection. So it admits a trace, then it's a finite projection. star u equal to 1. Okay. Then trace of u star equal to trace of u star 2. But it's prediction is equal to normal used in mathematics everywhere. Does not mean one is a, it has type 1 means minimal projections are a lot of projection and that will generate the whole thing. It will be effects. That's what we prove. See, it has some finite projection. For one and type 2 infinity. 2 MS type okay. Finite one algebra. Yeah. Two, identity is a finite projection. Identity is a finite projection. We have proved. Trace is there, so it's a finite phenomenon. It's not type 1. It's not type 3. It's not type 2 infinity. 1 is a, so this is a type 2 1 factor. G is type CC. That is no. It's all there. When you have a G which has infinite conjugate, we take this discrete only we are taking. G is this U. Now next one is M is a factor. Then is that something else? Sorry, not to go. I mean, this usual less than or equal to is not a totally order. You can have projection which are not comparable. Not can be anything. 。 In a total order. Okay. And this is not partial order in two sense. So what do you have to do? You are two projections. So for that, we already know such that U in M partial isometric such that used several times. To take collection of such that you may it's clear you stop and you okay. And this is we say U is less than equal to V. Okay. If I mean V is a partial isometric, kernel will be something here. Okay. I mean U is contained in V and the restriction. When we say U is less than or equal to V, it's like projection. Just the unit space contained in that and the rest it gives you. So okay. This is the natural order, clearly a partial order. And you can show that in every chain has a upper bound. Every chain means it's a totally ordered set. So you will have U's with kernel perf contained in the bigger one. So you have to take the union of all those spaces, which is well defined. Okay. On that you define a big U. You can define it using any one of them, wherever it is defined. Okay. And it will be consistent, it will be well defined because the restriction coincides. Okay. So I don't have to write it every. Okay. So please check every chain has an this is the maximal elements. Okay. And you have to max U. Okay. If you have, I mean, all these U's satisfies one U star U is less than the U star is less than Q. You only need one of them is equal to P. Then that gives a partial order. Okay, that's what you want to do. We want. Okay, this is the claim we want. So if not, we take the complement and define something and it will be clear. Okay. If not, so suppose so U star not equal to P. U star is less than or equal to not equal to Q. So this implies minus 7, 0. Okay. Now we use the then direct system partial geometry. Right? And we here. V star is less than or equal to Q minus Q star. Okay. There is a partial geometry. Now you just add U and V. And this is defined on the orthogonal complement of this range of that. U plus V V U star equal to straight will be 0. Okay, because their initial space is different, orthogonal. Okay, so U star V will be 0, V star U will be 0. And U star U and V star V are orthogonal. U star U is less than U star V is less U star V is less than some U star U is U star U, which is strictly less than P, and V star V is contained in P minus U star. Okay, so it is orthogonal to that. So because of that, this will be this V is non-trivial because that is non-trivial. It's not equal to 0. That is what this is. This U is not equal to 0. Directly means whenever I say here 0, okay, it's only not equal to 0. Okay? So this contradicts maximality, right? Maximality of U. Okay. It contradicts maximality, so it should be equal to P or Q, one of them. At least one of them. Okay. So I want next this one factor. So now we have its a total order. Now we want to prove that type 2 factor is the non-commutative analog of non-discrete, non-atomic measure space. Non-atomic measure space means if you have some set E, then you have a set F which is not equal to E, such that measure of this F is strictly less than measure of this for any such thing. Okay, there is no atom in non-atomic. There is no atom. Okay? So that's what I want to say. I want to say that it's non-atomic. So for that, I use I assume it's a 2-1 factor with a trace. Okay, our gamma G is one such thing. I haven't proved that it's true. Every 2-1 factor has a trace, admits a trace. I haven't proved. Maybe I will not prove, but our example has a trace. Okay, trace is unique in a factor. In a factor, not in a phenomenal algebra, you can have different trace. No, you can have a combination. In a factor, it is unique. Indeed, it's the other way also. If the trace is unique, then it's a factor. That's clear. No, you can have different convex combination and so M is a factor if and only if it admits unique trace. So it is easy to prove. If trace is unique, then M is a factor is, that's easy to prove. But the other way, 2-1 factor, every finite phenomenal algebra admits a trace. Of course, if it's unique, one is a factor. So M is a 2-1 factor with trace. Okay, trace. Just write it. Trace, linear functional with a faithful, weakly continuous trace. Okay. Then, given epsilon greater than 0, there exists a projection P not equal to 0 in M, such that trace of P is less than epsilon. Okay. Given any epsilon. All I have to prove is you take the infimum of all such trace of P is a projection in M. I want to show it's not equal to 0. That's what I want to show. Okay. So D. I mean, this is equal to 0. Sorry. I have to show that this is equal to 0. That's what I want to show. Less than any epsilon, it should be there. So suppose is greater than 0. Okay. Suppose this infimum of P in P is a projection is strictly greater than 0. Okay. Then I want to get a contradiction. That's all. Okay. I want to use this get a contradiction. Okay. Then, of course, D is the infimum. That means there exists a P in M. It cannot be only identity. Okay. I mean, this is a there are a lot of projections that we know. Okay. It cannot be just one or something. Okay. So the P in M such that trace P is less than D plus epsilon, greater than D, right? Given epsilon, given, I mean, this is the D is the infimum. So for given epsilon, there exists a P in M such that D is less than trace P by the property because the by proportion is less than D plus epsilon. Okay. Yeah. So we assume P is not equal to 1. If P is equal to 1, this is C. P cannot be equal to 1. That will means it's M will be C. I mean, there exists P such that something this happens. Okay. D cannot be equal to 1. Okay. Trace of 1 is 1. D cannot be equal to 1. So P is not equal to 1. So 1 minus P equal to Q. Okay. Not equal to 0. Okay. So there is one small lemma, which I will write it and then come back to this. Right? Yeah, yeah. So that's what I'm going to do. Yeah. Exactly, exactly. Yeah, something like that. In 1 minus T, I will get something. That's all. It's not working. For that, I take the formula, which is you should have said it before. If and P is in projection, then we have this is also this is a one dimensional algebra sitting in B of PH. Okay. This is also type 2. Proof defines P is not P equal 1 by trace of P. Of course, P is not then trace of P is not equal to 0 because it's faithful. On PMP. And PMP is, of course, PMP is a factor, and is this, why is it infinite? I mean, PXP also cannot have minimal projection, no? It's a factor. We have proved all that. Okay? It's a one-dimensional algebra is a factor. And PMP is a finite one-dimensional algebra. If it has, if that should also be, cannot have minimal projection. If that has minimal projection, that will be minimal that also. Right? It's under that, right? So this is a type 2 one factor. And it has a trace, so it should be finite, and it has a type 2 one factor. Okay. So because of that, so now what I do is the following. P such that the trace of P is greater than D and less than D plus epsilon. I do 1 minus P. Okay. Now there are 1 minus P equal to this. So yeah. This Q out. There is no Q. Okay. Q in 1 minus P. Yes. That's all, no? Then trace of Q is less than epsilon, right? Trace of Q. Why am I getting confused? Yeah. No, no, the trace of, I mean, you take X something Q. Q is also a projection. See, now if you, this should have enough projections. Okay. And trace of Q, the trace of Q is actually defined through this formula, 1 by trace of this, right? Okay. And trace of this Q will be less than that D plus epsilon in original M, right? Am I making any mistake? I'm saying that you take some Q here, then trace of Q will be less than D plus epsilon. Trace of Q will be, no, it should be easy. You have I want to produce some other Q which is between D and D plus epsilon. When you subtract, you get that's right. But P might as well satisfy that, no? Why? Yeah. I want to basically get a continuous projection. No, I think I have to quotient it, and then quotient is also a 2-1 factor. Because of that, I have to get it. So I'm saying that 1 minus P, 1 minus P. Hmm? Because if you don't have this projection Q, you basically get that for any projections, there should be a multiple of D. Otherwise, it will keep flattening for equivalent. No, I don't want to go into all that. It should be that, it should be straightforward. Uh, I think if I remember correctly, I think it should follow from this fact. M is a 2-1 factor. You hit it by 1 minus P. I mean, here I'm using P. This is just lemma. Take any P, hit it by this, you get a 2-1 factor. It has no minimal projection, so this cannot have minimal projection. Number one, and it has a trace on that. That's why it's a 2-1 factor. Okay, that is the reason. So if you take a projection, here P itself. No, P. That's okay. That's okay. P itself. Sorry. Now you take something Q in. Okay. Now this one, this P Q, this Q. I mean, if you have something in PMP, this PMP, all those X. So this Q will sit. Just look at yeah. Exactly. Sorry. Yeah. It is because of that. Sure. Yeah. It's not. P is not a minimal fraction. So that itself is enough. You don't need to question like that. Okay. You don't need to question. Yeah, this is a good lemma. Let it be. Okay. Yeah. You don't. Yeah. Good. That's all. I am not using factor itself. 2-1 factor. Okay. Yeah. So let's start. Yeah. Since P is not a fraction, it should not happen. Okay. This because of that. Yeah. Strictly P is strictly greater than 0. Okay. Q minus P should be strictly greater than 0. But then this will be less than epsilon, if you just see. So trace of P minus Q, trace of P is less than trace of Q and P. I mean, the all projection trace of Q and D. Yeah, good. I have to use the fact that it does not have any minimal projection. I was trying to use that here. Okay. So what we are, we have got that given epsilon. Okay, that's the assumption. So it follows from the fact that so given any epsilon, we can find a projection whose trace is less than that. Now we want to prove that given any number between 0 to 1, we will have a projection such that trace of that P equal to that number. So that's what I want to prove. Now we want to use that lemma. And we define the usual order. It's a partial order. Inclusion. The chain you have it, just take the union of those projections. If you have a chain totally ordered set of projection, one is contained in the other, just take the union, that will be a projection. So projection generated. Okay. That's the element. We want to prove that this satisfies the condition. Here I have to use that one to speak. Right. Okay. Then now trace of super. So direct in minus the trace of q is less than okay. Trace of q is less than this. Now, because it is contained in 1 minus p, q will be orthogonal to p. Trace of p plus q is less than r. This is a contradiction. Contradiction maximality. This is the onto function. Trace. This proves. I mean, what we have said is trace or 0 isomorphism. 1 with respect to that equal. Okay. I'll stop with this proposition. Proposition from all projections in M is a 2-1 vector, of course. Okay. To 0, 1 is an order preserving isomorphism. I mean, I write it like this. Quotient with equivalence. Okay. You identify with respect to equivalence. Okay. Then this is an order. This set can be identified with this set. That's all. Given any preserving isomorphism. I mean bijection. Okay. Proof of strictly greater than 0. So trace P is less than or equal to trace Q. Okay. And we know this is on 2. You can do 1, 1 with respect to this equivalent. Suppose P equal to trace Q. Then we know that This is the total order. The partial order we defined. So there exists a same proof. I mean, we already seen this proof. So there exists a U partial order such that U star U equal to P, and U star is the I mean, we know that this is that whatever the curved less than or equal to, that's a total order on this. Okay. So either P should be less than or equal to Q, or Q should be less than or equal to Q. We are assuming P is less than. Okay. But then trace of P, the trace of P equal to trace of Q. So trace of we have to prove that P is equal to Q. Okay. That is U star U is less than Q, right? So trace of equal to trace of U star U equal to trace of P equal to trace of no, we have trace of P, so that is equal to trace of. So this means U star is less than Q, no? So Q minus U star is implies Q equal to U star. Same thing. Okay. That's all to prove, no? I mean, so this is clearly order preserving. We have proved it's 1, 1. They are equivalent, and it's on 2. I think that's all. If I miss something, some lemma, I will prove it in the next class. Okay? Oh no, this is frozen completely.